Welcome everyone. For today's prep, we're going to look at a few more examples of sketching and describing polar regions. And this is going to be a helpful skill if you go into Calc 3, so I want to take some time with this. So we looked at the first part of example 3 last time. So for today, I want to look at the second part and then maybe jump down to example 4 as well. All right, so let's kind of go through the process again for how to sketch these polar regions. And usually we want to start with the angle. This kind of gives us a good place to start with. And as we're doing this, we want to remember the default setting for polar coordinates is a counterclockwise rotation around the origin. All right, so when we look at our theta angles, we've got the smaller angle here, and we want to think of this as like our starting. This is our starting angle. And then we've got this other angle, 3 pi over 2 in this case, and we want to think of this as where we end. This is like our ending angle. So let's first find where these two rays are on our polar grid. So pi over 3. Where is pi over 3? Well, that's one of our main angles that sits in the first quadrant. So pi over 3 is this one right here. Pi over 6 is the shallow one. And then pi over 4 is kind of right in the middle there. And then where is 3 pi over 2? Well, 3 pi over 2, these multiples of pi over 2, those are kind of give us the main axes. So we have 0, positive pi over 2, 2 pi over 2, and then 3 pi over 2. So 3 pi over 2 is the negative y-axis. So we just want to label those kind of starting and ending theta values, just to give us an idea of where to start and where we're going to end. All right, so once we have those rays plotted, then we can look at our values, our R inequality. And let's just consider starting with pi over 3. And we want to look at all the points on that ray that have an R value that is between 2 and 4. And these inequalities have an equal sign here, so it does allow for the possibility of including R equals 2 and including R equals 4. So we're going to make those filled in points. And R can be anything in between, so let's connect the dots. All right, so we're looking at this line segment. Actually, let me make that a little thicker. All right. Now let's do the same thing on the ray 3 pi over 2. So again, we've got the ray 3 pi over 2 extending from the origin this way, and we want just the points that have an R value between 2 and 4, and we're going to include 2 and 4 in our sketch. So an R value of 2 would be right here. So we're going 2 units away from the origin in the positive direction. And then R equals 4, we're going 4 units away in the positive direction there. And we want to allow for any point in between. All right. So now what we're going to do is we're going to remember our default setting, and that is with polar coordinates, we're going to go counterclockwise around the origin. So we're going to take this little line segment, and we're going to watch what happens as we rotate that as we rotate that around the origin, and it's going to sweep out our polar region. And to help us, let's just imagine taking this point. So let's start with the R equal 2 point, and we're just going to rotate that single point around the origin, and it's going to give us this semicircle. Well, let's do it for the R equals 4 point. We're going to rotate that counterclockwise around the circle. And again, it's going to trace out a piece of a circle there. And we could repeat this over and over again for any point on this little line segment. We could rotate that point around, and we keep doing this, and it's going to shade in our region for us. So essentially, when we do this, we're going to end up with this entire kind of a half-eaten donut here. So that's our polar region in this case. So if we pick any point inside this region, or even on the edge of the region, the coordinates for that point, it will have at least one representation where the R value satisfies this inequality and the theta value simultaneously satisfies this. Now, all these points in here have other ways, other polar coordinate representations, but it has at least one that satisfies both of these inequalities together. Now, one little note, we did have this equal sign here. So we had a filled in dot, and then when we drew the semicircle there, it was a solid line. Let's suppose that this was a strict inequality. So let's get rid of the equal sign portion. Well, in that case, we would have an open dot, means we don't want to include that. And when we trace along when we rotate around, we would make that a dashed line, just to indicate we don't want to include those points that sit on that edge. Same thing if, let's say, the pi over 3, if this inequality didn't have the equal sign, well, then we would make all the points that are on that pi over 3 open dots and dashed lines, just to indicate we don't want to include those as part of the region. Our region gets as close as it can up to that line, but it can't actually include points on that line. All right, so there is our polar region for that one. Let's try the next one. Now this one's slightly different because we're given inequalities in terms of Cartesian coordinates. And we want to sketch the region satisfying these points. And we're going to add a little bit extra to this. So let's also get the inequalities for r and theta. So that's what we're going to try to do. First, let's look at this inequality that x has to be greater than or equal to 0. So if x has to be greater than or equal to 0, well, let's pick a point. And remember, when we're picking a point, we want to think of the polar grid as kind of an overlay. It's a layer that we're just placing on top of our plane. And then the Cartesian coordinate system is another layer that we can place on top. So when we pick a point on the plane, we could think of this point as having a polar coordinate representation and also a Cartesian representation. And right now we're dealing in Cartesian coordinates. So x greater than 0, or x greater than or equal to 0, what this does is it gives us the right half plane. Well, let's actually be more specific. It gives us the right half of the xy plane. So if we were to sketch what that would look like, it's everything over here, including, because of the equal sign here, it does actually include that x equals 0 line, which matches up with the y-axis. All right, so the right half of our xy plane. Now, what about x squared plus y squared less than or equal to 9? What does this inequality look like? This is the one that's a little bit more difficult. So let's start by converting this inequality into polar coordinates. This will be easier to visualize if we convert it to polar coordinates. And the conversion kind of should be jumping out at you, is that x squared plus y squared is equal to r squared. So if we replace the x squared plus y squared with r squared, we end up with this inequality that r squared has to be less than or equal to 9. All right, so let's solve this inequality for just r. We don't want r squared, so let's do the square root of both sides. And that's going to give us r is less than or equal to positive 3. And when we're trying to describe a polar region, we don't necessarily need to have every single representation of the points accounted for. So it's enough to just look at positive r values. So we're going to make r to be greater than or equal to 0. And by doing the square root of both sides, r has to be less than or equal to 3. So essentially, we're looking at all the points in our plane that satisfy this inequality. The r value is somewhere between 0 and 3. So if we look at the edge, r equals 3, that's just a circle of radius 3 going around the origin. So this inequality, what it does is it's giving us a circle. Well, it's actually giving us the disk. So what would that look like? Well, let's find the circle of radius 3. So here's 3 units away from the origin. And then we're just going to look at the circle going around. And it's not just the circle. This inequality is describing everything inside the circle as well, because we have these inequalities. So we're going to fill this in. So what we're doing here is we're looking, so far what we've done is we've looked at each of these inequalities on their own. So the x greater than or equal to 0 inequality is just giving us the right half section of the xy plane. So it's given us all this. The inequality that x squared plus y squared has to be less than or equal to 9, by converting it into polar coordinates, made it a little easier to visualize, gave us a disk with radius 3, and a disk is the circle that's filled in. So it gave us this whole section. And if we're requiring that both of these inequalities are satisfied at the same time, what we're doing is we're looking at the overlap. So what is the overlap? Well, it's this half circle. And this is our polar region in this case. All right, so it's points over here don't work because they do satisfy this inequality, but they don't satisfy this other one. And points over here don't work because, yeah, they do satisfy the first one, but they don't satisfy the second one here. So this is really the same idea that we saw without really going into the overlap part of it, but it's really the same kind of thing up here. We looked at the r values that were between 0 and 2, which is this circle. And then also the points that were in between an angle of 0 and 3 pi over 4, which gave us this open wedge here. And then we were just looking at the overlap. The points that were in both of the regions simultaneously, and that was this intersection piece here. All right, so this is our polar region. Now, what about if we try to come up with inequalities for r and theta? Well, we've already got our r inequality. Now let's try to figure out our theta inequality. So we know our R value has to be between 0 and 3. But what about the theta value? So we want to figure out what's the starting angle and what's the ending angle. And while we do this, we have to remember counterclockwise rotation. So the default setting in polar coordinates is we're going counterclockwise. So when we do this, we want to imagine tracing through this region that we just sketched out counterclockwise. So just like going back up, we had our starting ray here, and then we went counterclockwise, and then we figured out where we ended. We want to do the same thing in this example. So we want to find two rays, and we've got one ray here, which is the negative section of our y-axis, and then we've got another ray up here, which is the positive section of our y-axis, and we can imagine just going counterclockwise. So what is the ray that gives us the positive y-axis? Well, it's pi over 2. Now what about the ray that gives us the negative portion of our y-axis? Well, it's 3 pi over 2. Now as we go through this, we're going to be going counterclockwise. So this ray here has to be our starting angle. So let's see what that would look like. So if 3 pi over 2 is going to be our starting angle, what's our ending angle? So we're starting at 3 pi over 2, and then we're going to rotate counterclockwise around, and then we're going to end up at pi over 2. Now this might be our first thought. This is going to be our theta inequality. This doesn't work because 3 pi over 2 is bigger than pi over 2. If you kind of follow the breadcrumbs here, 3 pi over 2 is not smaller than pi over 2. So this inequality doesn't work. So we need an equivalent way to describe this ray here, but we need a value that's smaller than our ending angle here. So we need this starting angle to be smaller. So what can we do? Well, we can add or subtract as many copies of 2 pi as we need. And in this case, we just have to subtract 1. So we're going to subtract 1 copy of 2 pi. And that's going to be our starting angle. So when we do that, if we subtract 2 pi, we end up with negative pi over 2. And our ending angle there is positive pi over 2. So an equivalent way of representing this ending angle, we could say 3 pi over 2. It's also negative pi over 2. So what we're doing is we have our starting ray, and that's the angle negative pi over 2. And then we're watching what happens as we rotate all those points on that line segment, and we end at pi over 2, positive pi over 2. So pick a point, rotate it around, and there. Pick a point, rotate it around, and there. Pick a point, rotate it around, and there. And we end up filling in that whole region, and the origin just kind of stays fixed, but it's still included. All right. So a little bit of fun with polar coordinates and polar regions. And in class, I don't know, we'll see. We might do a little bit more with polar curves, or we might jump over and look at some parametric equations. So maybe bring both sets of notes with you to class. We'll see you then. Bye-bye.